Next, we're going to take a look at reaction rates. And essentially what we look at in reaction rates is the change in enthalpy from our reactants to our product and how that reaction goes in the forward direction and how we can look at how the rate is affected by different variables in that chemical reaction. So reaction progress, which is generally the forward reaction from reactants to products. Now, some reactions do not proceed spontaneously at room temperature unless additional energy is added to start them off. So for example, energy is provided to a candle with a match. So we can provide some energy from that match using the striker, and we can light that candle with the match. So then we also can think about an example with methane. Well, again, methane can be lit with a match. Obviously, there's more energy released with methane, but the same match can give the candle a start and the methane a start. Now, generally, the candle would still require more heat energy from the match than the methane would, but they both require some level of additional energy to start them off, to start that reaction to occur. So we have to think back to our knowledge on the collision reaction theory. Now, essentially, the collision reaction theory, if you remember, that all of our molecules and particles are always moving, and essentially, in order for a reaction to occur, they need to collide. So entities are always in constant random motion, so they're always bumping around in all sorts of directions. Okay, a reaction must involve a collision of entities. So we have to have two entities bumping together, and most likely they're going to be two different entities that bump together. And an effective collision requires enough sufficient energy and a correct orientation. So we have to have them bump together not only in the right place, but with the right amount of force going in towards each other. Okay, ineffective collisions rebound elastically, so if two particles come in together, they will bounce off each other in opposite directions. So, if we take a look at our two examples here, and I'm just going to change this to a color that we can see that's a little bit visible. So when we look at our effective collision on the top, we notice that two reactants come in this case it's carbon monoxide and nitrogen dioxide, that they come in at the right angle, okay, and the right speed or the right amount of energy to create this activated complex. Now notice because this oxygen is located in the orientation that will jump onto this carbon monoxide, it looks like it's in the right location. Now what happens is these products then bounce off, and we have an appropriate effective collision producing carbon dioxide and nitrogen monoxide. Now if we think of this as an ineffective collision, which both of these would be happening simultaneously in a reaction, but if we look at an ineffective collision, again, we do not have the right orientation to line up to have an oxygen transferred. So because of that, these two entities simply just bounce off of each other, okay, in an elastic collision. They bounce off in opposite directions, and we still get carbon monoxide and nitrogen dioxide as our products. Again, our activated complex in the middle here, okay, these two here, are the same activated complex. However, this activated complex on the bottom did not have enough energy, or it didn't have the right location in terms of its collision for that to form the appropriate products. So it requires sufficient energy and orientation. So what does this mean? We talked about how a match can give enough energy to a candle, or it can give enough energy to methane. So we often require activation energy, better choose a color that I can see here, an activation energy of a reaction. Now, activation energy, we have to use this quite often. So activation energy is an energy barrier that must be overcome for a chemical reaction to move in the forward direction or to occur. So since we know that a lot of reactions are slow, why are they so slow? Okay, what is causing this to happen? Now, if we look at this activation energy in this diagram here, okay, we see that this would be considered an exothermic reaction. We see that there's a loss. If we look at our reactants as A and our products as B, we see that overall the net energy change is a negative value. This would be an exothermic reaction. So we know that it's an exothermic reaction, and the analogy of this is if you were to roll a ball up over this hill, and we're going to think of this green line as kind of a hill, that you needed to invest some energy to push that ball all the way up to the crest of the hill, in which once the ball was at the top, we would notice that the energy from gravity, or in this case our potential energy stored in our chemical bonds, is then all released going down the hill. Now again, we have a net overall change where we're farther down the hill than when we started, so we have a negative potential energy, or an exothermic reaction. Okay, but we had to invest some of that energy from pushing this ball up and over that hill. So because of that, we had to input some activation energy. So what we like to think of this as is the energy required for the reaction to start. Now again, in this example, we're looking at a net energy change of a negative enthalpy, meaning it's exothermic. Again, if we look at an example with our carbon monoxide and our nitrogen dioxide and our effective collision, okay, we see that we have some level of activation energy in order for these particles to collide appropriately in order to form our products. So what we see is we have carbon monoxide, nitrogen dioxide, and we had to input some activation energy. We call that EA, okay, our activation energy. Now, essentially, at the crest of our hill, we have this activated complex, okay? We see that at the crest of this hill is where these two components or two reactants have collided, and we have a net then drop in our energy change. We've pushed the ball up to the crest of the hill, and the rest of the way is pulled by gravity, or in this case, it's just a forward reaction rate. Okay, so we see that it equals negative 224.9 kilojoules for this reaction in the forward direction. So we see that it is an exothermic reaction and energy is released. Again, what we would see normally in a previous energy diagram that we've looked at is we would just see that the net energy change, again, is this negative 224.9, okay, and we see that there's a net change just like this. This would be reactants, and this is our products, which is no different from anything we've seen so far. What we don't see is there's this activation energy, which is this red line here, that provided the pathway, or it's the reaction pathway that occurred from our reactants to our products. Again, this energy had to be invested for an energy payoff. If we look at a different example, for example, the creation of hydrogen iodide, we see that we have hydrogen gas and iodine, and we see that if they collide effectively, we get our activated complex, and we produce hydrogen iodide. Now, when we look at this energy diagram here, we see that in general, we have a net energy change that is a positive value, meaning that this is an endothermic reaction. And when we have an endothermic reaction, we see that the activation energy far exceeds the energy that is paid off. So, for example, it would be like pushing a ball up a taller slope of a hill, getting to the crest of the hill and rolling it down the lesser side. You end up higher on the hill than you did initially. You end up higher up, meaning that you have, in this case, a higher potential energy, or you had to invest more energy, meaning you had to gain energy in terms of enthalpy to get to your products, meaning an endothermic reaction. Okay, so we've seen two examples. Again, that activation energy, you can think of it as pushing the ball up the hill, and there was a minimal, or a lesser, I shouldn't say minimal, but a lesser payoff from the energy that you had to invest, meaning an endothermic reaction. So in general, when we look at our two diagrams, we see that we have our reactants and our products, and with our endothermic, we have to have a greater activation energy. Again, this activated complex is your two reactants that have bumped together at the right space and energy and force together. Okay, so we have our reactants and our products, and the net reaction with our net enthalpy, okay, is going to be a positive value. We increased our enthalpy. So this is our reactants to our products. Okay, if we remember these lines, that is our endothermic reaction. Now, inversely, if we look at an exothermic reaction, we see that we have our reactants and it goes down to our products. Okay, we see that we have a negative enthalpy change. Okay, negative enthalpy change meaning an exothermic reaction. Notice the difference in energy required from the endothermic versus the exothermic. Our endothermic, we required a greater activation energy. Okay, we see this huge arrow here for our endothermic reaction, and our exothermic required a minimal amount of energy to go in the forward direction. So let's just take a look and see if we can figure out these few reactions 1 through 4 and just get a better understanding of identifying these as endo or exothermic and the amount of activation energy required. So in this first reaction, we see that our reactants are here and our products are here. Okay, this is what type of reaction? It is an endothermic. Okay, and we see that there is a fair amount of activation energy required. So I'm just going to go like this. I'll draw my arrow and I'll write my activation energy. So there's a fairly decent amount of activation energy required. Okay, then we look at example number 2. We go like this and we see that this is a loss of potential energy, or this is an exothermic reaction. Okay, we also see that there is sort of a small amount, especially in comparison to our first example, there's a fairly small amount of activation energy provided to this. Okay, we see a pretty good payoff. We definitely see that it's exothermic with a smaller relative amount of activation energy. Okay, let's look at number 3. Again, we notice that this is an endothermic reaction. Okay, endothermic reaction, and the activation energy here again is pretty minimal in terms of what we had to invest for our level of payoff. Now again, we had to invest more energy than we got from our products. However, you still have a change here that is endothermic. Okay, and if we look at our last equation or our last reaction here, we see that this is in fact an exothermic reaction. Okay, and we notice that there's a huge amount of activation energy required in this equation or in this reaction for this to go in the forward reaction. Now still, the amount of energy that we gained in our products by forming our products exceeded that activation energy. Okay, but it is quite amount of energy that had to be invested for that payoff to occur. Now, this is sort of the end of that little mini lesson on reactions and reaction rates. So you should be able to move on from here to take a look at the bond energy and reactions and how that works in terms of our energy changes and enthalpy changes. So at any point, again, if you need to go back, take some additional notes, do so now, and good luck.